Okay, so before we get back into the math, just a quick announcement. So y'all may recall several weeks ago there was a survey that I, in collaboration with some people in Psych and Neuro, sent out, and a very large number of students, thank you for your participation, a very large number of students participated. That information is very helpful. And you may recall that there was an extra credit attachment for completing the survey. So another such survey is going to be coming out this afternoon, as I understand it. The Psych and Neuro people are actually going to do the actual sending of it, but it's morally from me. So anyway, again, there's an extra credit opportunity here. Same amount, 0.02. Added to your final weighted average on the 4-point scale. Again, it should take on the order of 10 to 15 minutes to complete the survey. So anyway, for your consideration, just do keep in mind that there is that extra credit. You have a week from whenever the email goes out this afternoon to complete it. I think they're going to take it down next Monday. But I would encourage you not to wait until the last minute. It'd be really easy to forget about it. And you're probably going to have quite a bit of downtime, here and there coming up this week, possibly even in an airport, right? So anyway, at some point when you have a few minutes, I hope you'll take the time and go ahead and do that survey and get your little bit of extra credit there. Okay, right. So going back to the math. By the way, I apologize for my voice. I've got some sort of bug. Differential equation, system of differential equations, of course. Here's the matrix. And we talked about, a way to go through and solve these systems in some cases, specifically when the matrix is diagonalizable. And let me remind you what the big punchline was. The big punchline of our discussion there was this theorem. If you have this system, the matrix being diagonalizable, right? Then all you have to do is find the eigenvalues and eigenvectors. Of course, diagonalizable means you have a full spread, no missing eigenvectors. Okay? There you go. There's your fundamental set of solutions. So can we do that here? Well, the only twist in this example is that some of the eigenvalues and some of the eigenvectors are complex. And what difference does that make? Well, there's, one could have a long, complicated conversation about, this differential equation solutions thought of as in the vector space of complex valued solutions, CN valued solutions. And the final punchline of that, though, is, yeah, it's fine. Go ahead. Not a problem. Right, and so again, we're going to avoid the ugliness of that, and these eigenvalues and eigenvectors give rise to this fundamental set of solutions. Now, of course, we don't like this fundamental set of solutions. These solutions are not real, right? These two in particular are complex. So how do we deal with the fact that we have complex solutions here? We don't live in C3, we live in R3. We want solutions in R3, right? So we're going to play that whole real and imaginary components game again. This strategy here comes about from just taking appropriate linear combinations of these solutions. Quick side note, yes, I remember these are complex linear combinations, and therefore, again, we have to sort of we have to confess that there's this issue with, well, if you have complex coefficients, is that really allowed? And again, victimless crime, it's fine in terms of its punchline, and I don't want to get into the weeds of dealing with the details there. So, same punchline that we had before. We just have to take these functions, for example, this one, and let's just look at its real and imaginary components. Okay, this is just a little bit of algebra. How do I find real and imaginary components of this? Well, notice this is in a kind of a polar form, and this is in a kind of a rectangular form, and multiplying complex expressions that are in conflicting forms it doesn't really work so well. So we just have to either, take your pick. You can convert this into rectangular, or you can convert this into polar. Take your pick, right? So what I'm going to do is I'm going to try to convert this into rectangular. That's pretty straightforward. Notice that the e to the x, what you get from the real part of the exponent, that's already real. So let's factor out that e to the x. All that remains is e to the ix, which is cosine x plus I sine x, right? Euler's formula there. And so now I have two rectangular complex expressions. One of them's a vector, fine. Take it one component at a time. And as usual, we multiply as follows. Real times real gives us real terms. Right? Imaginary times imaginary also gives us real terms. Just don't forget that I times I is -1. Right? It's really easy to kind of inadvertently maybe cancel the i's or something. That's not how it works. Right? I times I is -1, not +1. And then likewise, real times imaginary gives you imaginary, and imaginary times real gives you imaginary. So, foiling it out in the usual way, what we find is that this solution multiplies out like that, which has very clear real part and imaginary part. Okay. So I hope that looks familiar. We did something really analogous to this back in chapter 4. It wasn't vector-valued solutions. This is vector-valued solutions, but other than that, it's pretty much the same thing. Okay. All right. Pause for questions. How are we doing? Yeah. Right. Yeah. Exactly. So in worrying about how many, do we have too few or too many solutions? Right. It is this conjugate pair of solutions. So you'll notice those are conjugates of each other. Right. They're going to have the exact same real and imaginary parts, except for a minus sign. And so we trade those two for these two. And they have the same spans, and they're both independent. And that's some tedium that y'all can check. Yeah, right. Anybody else? Everybody happy? Right. Okay, so what do we do if the matrices are not diagonalizable? That's going to be our next thing, the non-diagonalizable case. Everything we did up to now on solving these systems was for diagonalizable matrices. Okay, so we're going to try to do the same thing that we did previously. We're again going to try to decouple. Right, the big thing that we did last time with the diagonalizable case was we took our diagonalization. A was a conjugate of a diagonal matrix. Here, okay, we don't have that to work with. Here's our consolation prize. This matrix isn't diagonalizable, but at least it's Jordanizable. Right? Every matrix is Jordanizable. So let's put in our consolation prize in the same way that we did previously and keep our fingers crossed and see what happens. So we go through, same game, right? We're going to take this P and move it to the other side. We're going to take this P inverse Y. We're going to call it Z. So Y is equal to PZ. Do that substitution. Thus, we have, in fact, turned our original highly coupled system into a new system. And this system is better. You'll see an example here. Let's look at a system where the matrix is a Jordan matrix. Let's see here. Let's use as this Jordan matrix. Let's use that Jordan form matrix right there. So 4 is on the diagonal. A single basic Jordan block. What's the corresponding system? Well, that system is this. And notice it's not fully decoupled, so that's the disappointment. I mean, we were hoping, what worked out so great last time was that diagonalizing decouples. This didn't decouple completely. We've still got Z2s in our Z1 equation. We've still got Z3s in our Z2 equation. But our Z3 equation is decoupled. I can solve for Z3. That's a Calc 2 problem. I can solve for Z3. And once I solve for Z3, notice that at that point I know everything in the Z2 equation. And so I can solve for Z2. And once I solve for Z2, well, at that point I know everything in the Z1 equation. And so I can solve for Z1. So this strategy is called back solving, and it works out just fine, I'll say. There's some effort involved. I wouldn't say I like it, but it does work. And absolutely better than nothing in solving this system. Okay. Now, before I go and show you what the details look like, let me remind you that the big idea here was that we were Jordanizing. So we were viewing the matrix as being a conjugate of a Jordan form matrix. That's what turns our one system into our next system. And then here's how we convert back. Right? All of that structure, all of what we're doing here, the strategy is just like it was for diagonalizing decoupling. It's just, again, the consolation prize version. Okay, so you'll notice at the start of this example, we were given this arithmetic. We had a system given to us. Matrix A was given. And then I gave you some arithmetic. The arithmetic that was given is this, just to save you on multiplying a bunch of stuff out. So there's some free arithmetic. What you can realize, having noticed this arithmetic is true, is you can see that these matrices are inverses of each other. So this is a conjugation. And furthermore, this is a conjugation of a Jordan form matrix. Right? You got to recognize that that matrix is in Jordan canonical form. And so this arithmetic represents our Jordanization of the system. Okay, how are we doing? Is everybody on board so far? A lot of details to come. All right. Oh, you know what? While I'm here, I think this is a good opportunity for me to point out something to be careful of. You remember when we were talking about conjugations and change of bases and all that stuff, I gave you all some homework examples where, instead of, maybe A being, PD, P inverse, I didn't use A and D. Maybe I used like M and N. And then you've got to decide, if these matrices here are inverses of each other, then which one is P and which one's P inverse? And how do you tell which one is which? And remember, the big idea is you keep track by thinking about what are the actual bases being used, right? So this matrix here represents our linear transformation with respect to which basis, right? And likewise for the other one. And then you just kind of Lego the pieces together and it kind of falls in your lap. Okay. So along those lines, note that when you find arithmetic given to you, such as this, here's again that free arithmetic, just because it happened to fall in your lap with this one written as a matrix and this being written as the inverse of a matrix, that does not just automatically mean that that's the one that you should call P. Right? You've got a question in front of you. Is that the one that I should call P? Is this the one whose columns are the Jordan basis vectors? Or maybe the arithmetic just came to me in an unnatural, weird way for strange reasons. Maybe this one over here is the one that I really should call P. Maybe this is the one whose columns are the Jordan basis. Right? So, when you encounter a problem like this, you really need to think it through. Nothing about the way this question is stated tells you that these are actually your Jordan basis vectors. Right? Kind of, smacks of that being the Jordan basis, but nothing actually said that. Right? So what you've got to do then is think it through and think, all right, well, this represents our transformation with respect to what bases, and this represents our transformation with respect to what bases. You write that down. You can then fill in the blanks and see exactly what change of basis this is. This is change of basis from one direction to the other. And this one here is change of basis from the other direction to the one. Figure out which ones are which. Right? And then, based on that, you can infer which one of these matrices has columns that are your Jordan basis. Okay, so you'll notice when you look back through my old exam questions, there are multiple old exam questions where I give students some free arithmetic with no promise as to which one has the columns that you're looking for that are your Jordan basis. And I leave it to students to figure it out. And sometimes, just to see who's paying attention, I've deliberately put the minus sign in the wrong place. Right? So, again, I'm doing that because life is going to do that to you. And I want you to be on the lookout so that you won't get stung by that occurrence in your engineering futures. Okay. So, anyway, think it through. Always think it through. Always think through which matrix is which and which columns, therefore, are my basis. Okay. All right. Again, you'll notice a lot of that in my old exams. Okay, so let's go through and back solve this system. Now, before we do, just a quick reminder. Remember, these are the z's, right? We're looking for solutions to that system, and when we get those z's, we are not done. Our original question was to solve that system. I want to know the y's. If you know the z's and you need the y's, recall that at the end you're going to have to multiply by that P matrix. Okay. But that said, we gotta solve this system first. So here we go. There's our system. The strategy is to start by solving for Z3. There it is. There's that third equation. There's the solution. Knowing Z3, I can then look at my Z2 equation. There it is. Let's solve for Z2. Now this one's going to be a little bit more work. There's that equation. Here's the Z3 that I just solved for. Solving for Z2, notice that we have a homogeneous part. There's the homogeneous solution. And then there's also the particular solution. How am I going to find the particular solution here? I've got to make undetermined coefficients kind of guesses. And sadly, I do have an unfortunate coincidence to worry about here. Now, it's been a while since we've talked about 4.3, but you can see in what we have here, you can infer the characteristic polynomial. You can infer the magic number. And in this case, the magic number is a root of the characteristic polynomial. So that being the case, here's what our guess is. This factor of x is the result of the unfortunate coincidence. I'm going over that very quickly because, again, 4.3 is old news. Make sure that you can follow those details. You take this, plug it in, and what you find is that your A is that, and therefore your particular solution is that. Okay, just like in section 4.3. And like I said, a little annoying, right? A little bit of inconvenience in cranking that out, but it's just a matter of doing it. Okay, now that we know Z2, back up to here. Now that you know Z2, we can look at our last equation, our Z1 equation. Same story as before. Here's our Z2. Looking at that last equation, the Z1 equation. You gotta find the homogeneous solutions. You gotta find the particular solution. There's another unfortunate coincidence. Make sure to check through these details. Make sure that you can do that algebra. And what you end up with at the end of it all is that homogeneous plus particular is all of that. Okay, so this is what back solving looks like. It's a little tedious. But you can put that all together. Here are those solutions we found. There was our C3, the first one we found. Our Z2 was a little uglier. There it is. Our Z1, quite ugly. There's that. So the solution vector then is that. Now, you'll notice that I spaced out these solutions in a sort of an odd-looking way, but rewriting, because I spaced them out like this, I can rewrite that vector of solutions and see that it's all linear combinations of this fundamental set. There. How we doing? Is everybody okay? Right. And we're not done yet. Those are the Z's. Remember, right, the Z's are not what I'm actually interested in. I want to know what the Y's are. So I'm going to have to take these Z solutions that I just found. I'm going to have to multiply by the P matrix to get my Y solutions that I'm actually interested in. So here at the very end, and this, the arithmetic is matter of doing it, but don't forget this is our P matrix right there. Recopy that P matrix over here. Multiply one at a time by these Z vectors, and P times Z become those. Let me pause again. Does anybody have any questions about that part? Yes?
If you have a Jordan block that has more than one element in it.
Yeah, like multiple basic Jordan blocks inside of the Jordan form?
Well, have the example how it had two of the ones.
Yeah.
So if you have that, does that mean you'll always have an unfortunate coincidence?
Mathematicians always get a little scared when you hear the word always. Yeah. I believe it's going to work out that I think it's always, but I haven't thought through. I don't have a proof prepared, but be prepared for it to at a minimum often be an unfortunate coincidence. Yeah, that's right. I think it's always. Great question. Anybody else? Alrighty. So tedious. Now notice even in this solution that we did, we had some of the answer was kind of given to us, right? I mean, you could imagine that it might just come to you like this. Hey, here's a system of equations I want to solve. End of givens, right? You might not have this very convenient arithmetic given to you. This very convenient arithmetic over here told us what the Jordan canonical form was. That's not obvious from the A matrix. Not only does it give us the Jordan form, this allows us to infer the Jordan basis. That's not obvious. And how you would find, even if you knew the Jordan form, it's not clear that that's the Jordan basis. So, where does that come from? Okay? And I've commented on this problem previously, that we know how to find a diagonalizing basis. Diagonalizing basis, eigenvectors. That's it. Basis of eigenvectors. You know how to find eigenvectors. And so how do we find Jordan bases? We don't. In Math 216, I'm not going to show you a method where from scratch you can take any matrix and just produce the Jordan basis and the Jordan form. There is a method for doing it. It's just it's pretty involved, and it's beyond what I think is reasonable to do in this course. In years and years ago, I used to do a special case of it, in Math 216, and I don't do that anymore either. Again, it's time is short and tough decisions, and it didn't make the cut. So anyway, what are y'all going to do going forward when you find this situation? And the answer is you're going to let MATLAB do it for you. So there's the notation to get MATLAB to find for you not only your Jordan form J, but also your Jordan basis. I'll say your change of basis matrix P, the matrix whose columns make the Jordan basis, right? That P matrix, and so this syntax will do that for you, and that's unsatisfying, but it's really all we can reasonably do in Math 216. The actual analytical process is quite involved. Okay, all right. Now, before I go on, I want to show you all a neat special case. It's just really nice how this works out. It's very convenient, and it's also surprisingly common. There is a homework question in the book where, by the way, I think the book's presentation on how you're supposed to go about doing this is not particularly clear. Right? So I'm going to show you the trick that allows you to do this homework exercise. Again, it's an assigned exercise in section 6.3. that we're in right now. If you have a 2x2 matrix, it turns out that there's a shockingly easy trick, and that is it's going to take advantage of the fact that there's only one non-diagonalizable 2x2 Jordan form. They all look like this. I mean, there's only so many ways that you can fit basic Jordan blocks together. There's just not that much room to move inside of a 2x2 form. And as soon as you say non-diagonalizable, this is it. So what does that do for you? The fact that there's only one Jordan structure. This basis that we're looking for consists of an eigenvector. We can see it consists of an eigenvector because that first basis vector, its image is, there you go, a multiple lambda times itself. Right? But that second vector, we don't know how to find it. Can't find V2. Right? So here's the big trick. Don't worry about it. That's the big trick, right? So we'll see how this works out amazingly well in a second here. But whatever that first vector is, cool. The second magic Jordan basis vector that makes everything Jordanized just so, don't worry about it. Just pick any other vector. You could be random about it. You can be lazy about it. Pick a vector that has a lot of zeros in it to make your life simple. Something like that, right? Any vector. Now, obviously, it's got to make up a basis, so it can't be a multiple of V1, right? So, that would be something simple. But other than a multiple of V1, any vector at all. And I just want to show you why this is going to work. So whatever this other vector is, here it is. It's going to be some linear combination of V1 and V2, V1 and V2 being as they are a basis. So let's say that this random W vector we picked is A V1 plus B V2. And let's just see how the algebra works out. Let's see here. Let me do this for a second here. Start off by observing that that matrix up there, the Jordan form, what we know is the Jordan form tells us this information. Right? Keep in mind the Jordan basis being the inputs. Right? Same Jordan basis being the outputs. The matrix is just telling us how the outputs are linear combinations of the inputs, right? In the usual way. So this matrix tells us these coefficients for outputs in terms of inputs. Okay. Now, I would like to know, okay, well, yeah, but what about with respect to the W basis instead of the V basis? Well, the W basis I'm going to need to know about V1. Cool, I already have it. And I'm going to need to know about W. And, well, W is a combination of V1 and V2. If I want to know what does A do to W, well, multiply it out and kind of collect terms around as needed, and here's your result. And the nice punchline then is, let me zoom. That information gives us this. Right, those two equations. Because notice what we have is our input vectors, the W basis, the W script W basis consists of the vectors V1 and W. That was our premise. Right, we're writing them in terms of the output basis. Well, V1 and W. Well, there's no second term up there, but anyway. There you go. Those two equations tell us that with respect to the W basis, forgot to code that in. There we go. And with respect to the W basis, here's the matrix. And notice, upper triangular, back solvable, totally fine. And we can use this basis to go about our business. It doesn't Jordanize, right? Conspicuously, that is not necessarily 1. So I can't say that that's a Jordan basis. It's probably not a Jordan basis. But I don't really need it to be a Jordan basis. I just need it to be back solvable, and you can see that it's going to be. Right? If I write out my Z equation here, my Z equation is Z1 prime equals lambda Z1 plus BZ2, and Z2 prime equals lambda Z2, lambda Z2. And I can solve for Z2. And once I know Z2, I can solve for Z1. Okay, so quick for example. Let's take this system right here. So solving our usual homogeneous linear constant coefficient system. Here's my matrix. If you go through the algebra, you can confirm without too much trouble that we only have one eigenvector, so this is not diagonalizable. I don't know how to find a Jordan basis. Right, so, problem. But no problem, really. Take that one vector, take that one eigenvector, combine it with any other vector, and I've pulled this one out of thin air. No particular reason. Negative 1, 1. I did have to think through and make sure it's not a multiple of the first vector. Sure, absolutely. But use that as a basis, and let's do the conjugation, with respect to that basis, and that being then your P matrix, and conjugate it through, and here is your new matrix, and notice that it is upper triangular, and it is therefore back solvable, and so you can solve for the Z's, and multiplying by P, you solve for the Y's. Just like in our previous examples. So anyway, I think it's kind of a nice trick. Use your eigenvector, pick any other vector, doesn't matter, and go about your business. It works just fine. Okay. Again, so this is not in the book. I think it's a nice trick to know, though, and it will be very relevant in that one homework exercise that requires something like this. Okay, so I'm going to go on and I'm going to show you another method for how to solve non-diagonalizable systems. I want to segue into this method with a silly joke. I think this is actually relevant, so forgive me in advance for this, but it does actually kind of segue nicely. So here's a true fact. If you take the limit as x approaches 0 from the right of 8 over, let's see, what is it? 8 over x. you get infinity. I hope y'all remember your Calc 1 or Calc 2 whenever you do this kind of thing. Right? Everybody remember that? Okay. So one could imagine a unfortunate situation where a student looks at this and says, "Oh, okay, I think I see how that works," and then they get onto the test and they need to compute the limit as x approaches 0 from the right, and it's a very similar question, and they do that, right? So I mean, wouldn't that be sad, right? It's a dumb joke. Sorry, I apologize, but you'd be surprised. We're about to see something almost this ridiculous actually work. So here it comes. Almost that ridiculous. So here's a differential equation that you'll recognize. If y prime is equal to a y, then a solution to that is y equals e to the ax. Right, and notice my arrow goes this way. I'm not saying that every solution has to be that one solution. No, of course not. There's lots of solutions. I'm just saying that function, if you plug it into the left, does work. Okay. Well, okay. So let's extrapolate irresponsibly, like in the joke, and look at this equation. You could imagine speculating, maybe, that, what about that? Right? I mean, again, come on. That doesn't make any sense. Right? You can't raise e to the power of a matrix. Right? Even if you could raise e to the power of a matrix, just because the scalar equation above worked out, I mean, can you possibly expect this to work also? Right? It looks ridiculous. But it totally works. And it's just really neat how this this works out. So I have a lot to develop for you now. Very first thing I have to do is I have to persuade you that, raising e to the power of a matrix is not just garbage. Right? Are you allowed to do that? We have never done anything like that before. The only things we have ever stuck into an exponential were numbers. Right? Real or complex, but numbers. So, again, you can't raise e to the power of a bicycle. Can't raise e to the power of, Wednesday. It doesn't make any sense. Right? So, can you raise e to the power of a matrix? And the big idea is, yeah, sure. How about this? Let's define matrix exponentials by a Taylor series. Right? In fact, we've done this before. We defined e to the power of a complex number in the same way. Right? Before we wrote down this Taylor series, we didn't have any sense of how it ought to make any sense at all to raise e to the power of a complex number. Taylor series makes it kind of work out reasonably. Well, if we can extend the application of exponentials with Taylor series, in that case, why not in this case? Hey, now this is just a definition, but it's a perfectly plausible definition. It's not contradictory or anything. So this is going to be our definition for matrix exponentials. And you'd be surprised how much you can do with this. So first thing I want to do is let's look at this very special matrix exponential, e to the power of x times a constant matrix. I'm going to let a be a constant matrix here. Well, taking that and plugging it in for m, that formula turns into this. Oops. Turns into this. And now let's take these derivatives. We'll take these derivatives one term at a time. The derivative of a constant, of course, is 0. That's not a problem. Here, I've got x times times a constant matrix. Now you could think about this one term at a time. If you look inside of this product, there's a common factor of x in all of the entries. When you take those derivatives in each of the entries of this matrix, you've got a constant times x, and you're just going to get the corresponding constant. So that derivative is just a. And likewise for the rest of these terms, you get like that. And then take a common factor of a out of each one of these. And what you have left over is exactly, you will notice, that, namely e to the xa, and therefore e to the xa, this weird little matrix here, this matrix exponential is a matrix whose derivative is a times itself. And where have we seen that before? That's the differential equation that we're trying to solve, right? We're looking for something whose derivative is a times itself. So that matrix does it. It doesn't seem like this ought to work, but there's really no problem in making this definition and therefore getting an answer. Now, this might seem completely, abstract and pointless. After all, am I actually going to evaluate these things by computing this infinite series? Do I have to add up an infinite series of matrices every single time I want to use this? Now, it's going to turn out we have some better tricks than that. We can develop the tools more powerfully. But the big idea to realize is that this actually does work. And by the way, notice it works just as well if you multiply by a constant vector. Right? In fact, here let me stick that in up here. I could replace e to the xa with e to the xa times a constant vector y naught. Right? The calculation goes through the same with just a constant vector y naught on the right. And so sure enough, that multiply by a constant, and it still works. So this is a solution too. Not hard to check that not only does this satisfy that differential equation, but it's real easy to check that e to the power of the 0 matrix is the identity matrix. That's something I'm going to ask you all to plug in for yourselves. It's just a matter of plugging in. But e to the power of the 0 matrix is the identity matrix. And as such, this also has, satisfies this initial condition. So what we have then, it seems too good to be true, but for any initial value problem, there's the solution. Right? So all that back solving business, I mean, you don't really have to in a sense, because matrix exponentials do it automatically for you. Right? So that's a really, really cool trick. Okay, now of course, obviously there's got to be something, there's a catch to this. It does remain that the fact that this works is nice and all, but as of the moment, the only way we know how to evaluate matrix exponentials is with an infinite series, and that's not tractable most of the time. So we're going to have to figure out how to evaluate these things. But once we do, when you have an initial value problem, or even if you have a differential equation, matrix exponentials are the answers. Very handy. Very cool. Okay. Here's another theorem I'm going to leave as an exercise for you all to prove. But so knowing a solution to an initial value problem is one thing, but if you want a fundamental set of solutions, you can get that by taking any basis for Rn, and multiplying by these matrix exponentials. And this thing that results will always be a fundamental set of solutions to the system of equations. That's going to be a powerful tool in terms of actually, in practice, solving these equations. What basis do we pick? You could, I suppose, pick the standard basis. I don't advise it. The standard basis is going to be a bad choice. But I mean, that it would technically work. It's just it wouldn't be very convenient. That's going to make your life really, really hard. Next thing you might be thinking is, hey, I got an idea. How about eigenvectors? Let's pick a basis of eigenvectors. Well, if you have a basis of eigenvectors, then that works out just fine. In fact, if you apply that theorem to an eigenbasis, you get the previous result that we had from last time. You'll reproduce that old theorem that just look at the eigenvalues and the eigenvectors and plug them in, and you'll get that exact same fundamental set of solutions. So using eigenvectors is a good choice. But now, thinking further, what about if the matrix is not diagonalizable? Remember, that's really our big topic for today in the non-diagonalizable case. Now what basis do you pick? Well, standard basis, again, bad choice. Eigenbasis would be great except for the fact that we don't have one, right? And so a reasonable thing to try is what's our consolation prize, right? When it's not diagonalizable, at least it's Jordanizable. The Jordan basis is our sort of like, it's the, at least I could do this. It turns out if you use a Jordan basis, everything's going to work great. And there's a little bit of work that we have to do to develop that, but a Jordan basis is going to be our trick. So going forward, you're going to pick the Jordan basis. We need to figure out how to multiply matrix exponentials times Jordan basis vectors. And having done so, we will have a fundamental set of solutions. Okay, so that's our big picture strategy. Here's an equation that I don't want to prove in this class. It's not hard. It's just a little bit of algebra. There's a little bit of ugliness that we need to deal with if you want to go through and prove this equation. But it's not that hard. The big idea is approximately that we're going to rewrite e to the xa as being itself, and then multiply and divide by if you take this expression, noticing that what I have right there is just a great big zero. If you take that and multiply it out, you have to check that the algebra that you would like to do actually works. It's annoying. But if you multiply that all out, you get this as a result. Feel free to play with that if you'd like, or if you want to see the details, come talk to me in office hours. But we're going to take this equation and just run with it as is. And the big idea is that if you are looking at an eigenvector, if you are looking at an eigenvector, then this equation works great. This is awesome for eigenvectors because multiplying by a matrix exponential, in other words, making solutions, the big magic trick that we want to be able to deal with, boils down to understanding what does a minus lambda I do to said vectors. And of course, eigenvectors, it's super convenient what a minus lambda I does to an eigenvector. Eigenvectors are in the null space, right? They're in the kernel of a minus lambda I. So a minus lambda I times an eigenvector is just 0. So that term just disappears. Likewise, that term just disappears. In fact, all of the terms, all of these infinitely many terms, they all just disappear because V is an eigenvector, and therefore all you're left with is just e to the lambda x times the eigenvector. Great trick. Very cool trick. Applying this now to a Jordan basis vector, there's a little bit more work that we have to do, and we're not going to make it time-wise. But that's the next thing that we're going to do on the Monday after Thanksgiving, right? So a full week from now. But what we're going to be doing is we're going to be looking at these as being Jordan basis vectors. We're going to try to figure out what does a minus lambda I do to a Jordan basis vector, and therefore what can I infer that this equation tells me about matrix exponentials times Jordan basis vectors. Y'all have a great break. See you later. Have a good one.